I'm going to make a T-table and then go graphically over to a histogram to see some familiar shapes show up. Hopefully. Else we got some really crazy deviant data today, which I'm guessing we're not going to get. Even though on the ride in today on Sawyer Uplands Trail, I almost ran over a perfectly formed adult, I think it was a male dragonfly, sitting in the middle of the trail. I have never, in 30 years of riding a bike on dirt trails, seen a dragonfly sitting in the middle of a trail, perfectly formed, perfectly healthy. I hope that's not an indicator of the kind of data we're about to get. Hopefully not. Anyway, how many, let's do it this way. We're going to collect data a lot this way. How many of the trials that you guys just did you get absolutely no red cards? In other words, you threw 5 cards and they were all black. We got one back there? We got one? Just the one. Okay, good. Oh, we got 2. 2 out. And if you guys did this at home too, throw those results in as well. Tell me your name in the back again.
Jake.
Jake. Okay, Jake and Allie both got 1, so that's 2 total. 2 in there. How many of you, when you threw the 5 cards, got 1 red and 5 black? I don't care how they came, whether the red was at the beginning, in the middle, at the end, as long as it was just 1 red and 5 black. Use fingers to show me how many times that happened too. So just so I can count it up. So if it happened twice, go like that. If it happened 5 times, do it like that. If it happened 10 times, use both hands.
Sorry, I got 2.
You got 2 of these. That's okay. That's okay. We'll get this all together. See? People complain about my damn deck. See this? Of course I'm seeing this too. So 1, 2, 3, 4, 5, 6, 8, 10, 11, 12. 12. Good. Good so far. How about 2 red and 3 black? Fingers and hands. Might need 2 hands for this one, maybe, depending on how many trials you did. 1, 2, Linda.
I'm not understanding.
So you threw 5 cards.
Right.
And then there's a certain number of red cards in those 5.
Right.
And you do that, did you do that experiment a number of times? So you threw 5 cards, counted the red, then threw 5 cards, counted the red, threw...
No.
You just did it one time?
Yeah.
Oh, that's okay. Then you did it one time.
No, we picked like you did.
Mm-hmm. 5 times.
Yeah.
And you call that 1 set.
Okay.
And then I'm saying, in how many sets did you get exactly 2 red cards?
Okay.
Is that cool? Does that make sense?
Yeah.
So how many did we get? I'm sorry, I didn't get the count.
So 1 set.
5, 7, 8, 12, 13, 16, 17, plus 6 is 23, 26. Did I get you? 26, 27, we're going to throw in there. 28, 29, with a number this big, it's not going to make that much of a difference. 32, plus 5 is 37, 38, 39, 40, 41. Thank you, friends. Thank you. Okay, good so far. How about 3 red, 2 black? 3 red and 2 black. How many times did that happen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 plus 7 is 31. Excellent. 4 red, 1 black. So in how many trials did that happen? I think, Linda, the confusion is 2. A trial is throwing 5 cards. No, it's okay. It's okay. This can be weird. A trial would be throwing 5 cards. This is why I made the quiz for next week, because I figured it would be a nice extension in case it didn't make sense in class. You can look at it again. Totally get it, my friend. So in 5 cards, we got 4 red and 1 black. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Sean, will you add 3 to the 1?
Of course.
Thank you.
Thank you. Love data. And all red. How many all reds did we get? We got 2. We got just 1, Chris?
1. Yeah.
3. 3 altogether. All right. Anybody have any that they didn't do while we were doing the collection? We can throw them in now. Because I want to graph it too. Because what Excel will do for you on this quiz is do all of this automatically as you sit there and hold the F9 button down. Again, one of the beautiful things Excel can do. I give you a hint on the quiz. If you don't want to sit there and hold the F9 button down, put something heavy on it and walk away, get a drink, come back. I use that old Swingline stapler, big heavy steel thing, just put that on there, let it run all day. Okay, there's also more clever ways of doing it if you know VBA, which I don't. So let's graph this thing. I held off on the scaling. 41, let's go to 50 by 10s. How's that sound? 30, 40. Okay, draw some red bars in there so we can see what we're looking at. We got 3 occurrences of not getting any red cards. Somewhere in that neighborhood. 15 41, 31, cute voices today, and 3. Who just showed up? I just love this crap. I love this. Who told that to go there? Who told that to be there? Random chance told it to be there. Can anybody explain it mathematically, why the bell curve showed up? Mathematically? Give it a whirl. Why would the bell curve, or why would a curve that looks kind of like this? No, forget the bell part. Why didn't this happen? Or this happen? Why is there more here than here? That's a better question. I think it's also a more approachable question. Why is there more in the middle than on the ends? Please tell me your name again.
Brian.
Brian, go.
Because it's closer to the probability of 2%.
Good. Now, it's closer to the probability of 50%. What Brian just told me was, if I throw 5 cards from a fair deck, how many of them should be red, on average, over time? 2.5. Half of them, right? So 2.5 is right here. So it makes sense that the lion's share of what you're seeing should happen right in here, because that's where your average should be. Is that a great? We'll use that, that's good. Here's your average. Now I'm going to be a total bastard and call this mu. And not, good, good, total bastard, right? Why am I being a bastard calling that mu? How dare I?
I don't remember what mu is.
What's mu? The average of the what? The population. Whew. But you see, we have a little bit of prior knowledge of these card decks, don't we? I can call this 2.5. Because unlike what Brandon said earlier, he said, how come you're never going to show me that deck, right? How come you're never going to show me that deck? Well, because you can't, because it's your population. Well, I just handed you the population, and you know it's a deck of cards. So you have some prior knowledge, right? If I needed you to, you could calculate sigma too. Don't worry about that right now. Don't worry about that right now. Okay, we can also approximate it using the graph, which is a more fun thing to do. But this is fiction, really, if you think about it. That's fiction. You don't know what that is, usually. But can't you infer what it is from that graph? Remember? Now this is where you go back to the tail end of 243, the central limit theorem. When you draw a sample, the sample has an average, yes? Your sample has an average. The average of that sample, we call it x bar, is very close, if you sample correctly, to whom? Who I've already mentioned today. It's very close to mu. Now very close is relative, we'll talk about that momentarily. But x bar should be close to mu. Did anybody calculate what x bar is on this? Anybody calculate what the x bar actually is? You'd have to do a weighted mean calculation on this, right? So this times this plus this times this plus this times. We'll do it in a moment. We'll fire up the machine and we'll figure out. We'll do it together. Let me turn the document camera on actually. Get this thing warmed up if we need to use it. Go ahead, Allie.
Mu stands for the average
Of
of
the
sample.
population. We're going to get x bar from our sample. That's what I'll throw the document camera on. We'll take a look at how to, in case you don't remember how to calculate that kind of stuff, we'll remember how to do it on the TIs. So the problem is, since this is a fiction and we don't know it, we have to pretend we don't. We have to realize we don't know it in general. So the best we can do is get the average of this sampling distribution. Now here's the kicker. You guys just did 5 cards and you counted how many red cards you got, right? That was one sample of size 5. Sample size 5. When you put all of your samples together to get this, you get what's called a sampling distribution. A distribution of all the samples. And that's when the bell curves tend to show up, regardless of what the original distribution looked like. The original distribution of pulling cards out of a deck is 50-50. It's a rectangle. But yet, when you start sampling, you get a bell curve. Now, Brian nailed it on the head as to why there's more in the middle. Because the average is closer to the middle of this. The average of the uniform distribution is rectangular, but it's still in the middle. It's in the middle of a rectangle, right in the middle point. Okay? So, let's do this 2 ways. You guys, when we did the experiment in class yesterday, were upset. Not upset. You were critical. Good for you. You said, the deck is rigged. And I said, prove it. And you said, it's 10 o'clock, let me go to my next class. And I said, go to your next class. I want you to now, you're back in here and I got you for like an hour and a half. Prove it to me, based on that data, that the deck is rigged. because no red card. And you can't prove it 100%. Prove it pretty well though. Prove it to me that the deck most likely is rigged based on this data. Use a probability, if you would, not an average. We'll get to the averages and stuff like that momentarily. But use pure probability, because that's the last thing we were doing in 243 together.
So if you add up all of the F column,
How many trials did we do? Let's see, 72, 102, 108, did I do that right?
it would be 3 into 108. That would be the probability of that happening.
You hearing this right here? First of all, did I add that up right? Check me on that. Always check my arithmetic. If you've had me in class, you know this. If you haven't, I can't be trusted. Allie, go.
What does the E thing stand for?
Oh, add up. Big sigma.
Okay.
Big sum. Sorry, bastard move. Big sigma means add everything up. We see it every once in a while in here too.
Yeah, that's right.
You're right.
It's 108. Very close to 100. I should have lopped off 8 data points and just called it good, but that's okay. So, what Brandon is saying is, okay, rule, I'll pretend that deck you were pulling from is fair, because why would I suspect anything different? Why would I suspect it's not fair? Let's just pretend it's fair. Let's assume it's fair and go with that. Okay, so assuming it's fair, what is the probability of getting no red cards out of 5 from a fair deck of cards? That's the question we have to answer. If indeed it is fair, how likely or unlikely is it that we got no red cards? Well, we should have averaged 2.5 red cards per 5, or half the time, right? So the way you can do that with a Monte Carlo approximation, which is what you guys just did, you just simulated the experiment 108 times, is count out of the 108 trials of 5-card deals, how many times did you see no red cards? If this number is large, then you just sit there and be happy, because it's something that should have happened, because it has a large probability, right? If something has a large probability, it should happen often. And you shouldn't complain about it when it does, correct? But if something has a small probability, theoretically, and then it happens, you have to question that. I'll come back to that momentarily. So out of our 108, how many times did we get no red? 3. What does that come out to be?
2.7.
Exactly, a little bit less than 3%, 2.7%. We should only see this about 2.7% of the time. Is that big or small?
Small.
That's ridiculously small. Which makes me sit back and go, well, I can think of 2 explanations for this crazy event. 2 explanations, maybe even more, but I can think of 2 right off the bat. What's the first explanation you can think of? You already thought of it. It was all planned. The deck was rigged. Deck was rigged. What's the other explanation? Possible explanation. Allie.
I feel like I only did 7 trials and I got 2 with no cards, so we might not have done enough trials.
She only did 7 trials. She got 2 with no red cards. That's a 28% chance, isn't it? Because a 1 in 7 is 14. So Allie would come to a different conclusion, wouldn't she? She'd come to a different conclusion and go, 28% is a huge percentage. That's roughly 1 in 4, a little bit more than 1 in 4. Nothing wrong with that at all. You see why it's so important to do a lot of trials?
I did 20, I didn't get any of them.
20 got none! Put you 2 together and all of a sudden you're getting a better picture, right? You put you 2 together, you put 108 together, you get an even better picture. You go to Excel and use a Monte Carlo simulation, do it 10,000 plus trials, you're like, oh, I'll see what's up. So one explanation is something's up. The other explanation is nothing's up. The deck is totally fine and we just experienced an outlier. Which happens. Yes. But it shouldn't happen often by the definition of what an outlier is, right? Outliers should not happen often. Allie, you got an outlier of outliers. But it happens. It does happen. 2.7% is not 0. It does happen, just doesn't happen that often. Fair enough? Is that good? Any questions you guys have right now? Hopefully you're starting like, oh yeah, it's 243 coming back. I'm getting it again. I'm starting to see it again. Coffee. Question. Could we have gotten this result without doing all this work?
Yeah.
Yes, we could have. Can somebody explain to me how we could have gotten, we wouldn't have gotten this exact result, but could we have gotten close to this result without doing all of this work? Tell me your name one more time. I keep wanting to call you David.
Jake.
It's Jake.
So
It's in front of you.
there was 50% chance of getting it first try.
50% of getting it the first try, so half the first try should be red.
Right. So then there's 50% chance of the next one.
Half of that half should be 2 reds or two blacks. We'll go 2 blacks. Half should be 2 blacks.
And then you continue it 5 times.
The third time, half of the remaining should be black again. So that's a half of a half of a half. Fourth time should be a half of a half, a half, a half. Fifth time should be a half to the 5th power. What numerically is 1/2 to the 5th power?
3.125.
Oh boy. Uh-huh. It's not exactly the same as, it wouldn't be exactly the same. Because we only did 108 trials. This is why when you go to Excel, you're going to do 10,000 plus trials. Which sounds awful until you realize you push down the F9 button. It's like all of you working very, very, I'm guessing in less than a minute you'll get that many trials. Maybe a couple of minutes, a couple, 3. Like I said, put the stapler on there, walk away, get a drink, come back, it'll be done. With technology. So we could have done it, right? We could have done it directly. But you have to know that 1/2. And that is part of 244 is you have a supposed probability that you assume is working. In this case, 1/2. That 1/2 is very important because you're assuming that half the deck is red and half the deck is black. When you apply the assumption that half the deck is red and half the deck is black, and you realize that this is the chance of getting all black cards, you find it harder and harder to believe that the deck is fair. Because it's so rare to see a deck that's all, to see 5 draws that are all black. Just like it would be hard to believe that 5 cards will come out red. Symmetric, right? That's also half to the 5th power. I'll give you 2 examples of how I've used this in my everyday life. And then we'll take 5, because we're getting close to that break time, yes? The first happened about a year ago. The second happened about 3 months ago. A year ago, there was a kid speeding through my neighborhood. He ran a red stop sign. And anybody ever seen The World According to Garp? Old movie with Robin Williams in it, rest in peace. There's a scene where there's a kid, or a guy, I forget if it's a kid or a guy, that always speeds through Garp's neighborhood. Garp was played by Robin Williams. And Robin Williams has kids. And he chases the guy down to yell at him. I didn't have to chase the guy down. He parked 3 houses down, so I walked down to him like, hey man, just want to let you know there's a stop sign back there. I know it's kind of hard to see. He said he put it in a weird place. And he's like, oh, I never run that stop sign. I'm like, well, you just did. I watched you do it. I was sitting on my front porch shucking corn when you did. He's like, oh, I never run it. I'm like, dude, okay, so you just did, first of all. And secondly, that means either 1, you truly don't usually run it and I witnessed a rare event, or number 2, you run it frequently and I witnessed your common behavior. Which is more likely? And at this point, I'm seeing the kid's face just turn green. He's like, oh, I just came from school. So that's the first event. What's more likely, that I witnessed a rare event? Or that he always does it and I witnessed the commonplace event? More likely, yes? More likely, right? Okay, so that's a perfect example of a p-value in everyday life. If you witness some, and you know what's amazing? This also, speaking of Robin Williams, he died related to depression, as we all know now, which blew me for a loop. I mean, he's one of my comic heroes. It's so often the symptom of a depressed person that they feel what they're feeling is unique to them, and that nothing can help that feeling, yeah? Nothing can help that feeling. But that's just it. So many people feel exactly that feeling, but you're so sheltered from it that you think your p-value, so to speak, is teeny, teeny, tiny, when in fact it's influencing way more people than you even realize. But the depressed person can't process that. They can't do that statistics, obviously, because they're depressed. So isn't it amazing, and sad at the same time, that the same logic I applied to this kid running a stop sign in my neighborhood also applies to the way a depressed person processes their dark spot. Not to totally bum you guys out this morning, but there is that as well. And it's being able to metric that.
That's why I'm so bad at math, because I'm depressed.
Let's take 5! I don't know how to answer that, Chris. Let's take 5. Sean. I'm joking.